the Department of Alumni Relation and Director at Maharishi Dani University, Rohtak from 2016 to 2020. He has been awarded for his excellence in teaching and research by the Indian Society of Information Theory and Application in 2018. He has been chairperson and member of various academic and research bodies. He has vast experience of teaching various undergraduate and postgraduate courses. Professor Kumar has research experience of about 32 years and he has more than 30 research publications. He has participated in more than 80 national and international conferences, seminars, and workshops. He also evaluated for expert lecture in more than 70 conferences organized by institution bodies in India and abroad also. He has been a deputy coordinator of UGC SAB section to the Department of Mathematics from 2012 to 2017. He has also been convener, coordinator, in charge, and member of various committees. He guided more than 25 PhD MPhil students for his dissertation work. Welcome to you, sir.
Thank you, Dr. Poonam. Very good evening to each and everyone on the board. I'm thankful to the Deputy Coordinator for introducing me in a very well way, in a manner, and I welcome all the participants who are on the board today in this evening. Today is the third day of this Gyan course, and I humbly request all the participants that you please keep your mic muted so that there won't be any echo. But whenever you wish to have query, any answer, you want to ask any question, then of course you can unmute your mic. And at the end of the session, you must keep your video on so that we can have pick of the session. So again, good evening to all of you on this third day, 16th of March, 2022, on the occasion of the Gyan course being conducted by Department of Mathematics, Maharishi Dani University, Rohtak, on stochastic processes theory and its application in medical sciences. As you know, since from the 14th of this month, that is from the first day only, we are going through the fundamentals of stochastic processes, and of course we have also gone through some basics applications of the stochastic processes, and Professor Rao, who is our foreign faculty, he has continuously discussing about the stochastic processes, their fundamental, their applications, and of course a lot of examples have been taken up. So I start with the my lecture. The screen is visible to all of you?
Yes, sir.
Yes, Poonam?
It is visible, sir.
Screen is visible?
Yes, sir.
Okay, thank you so much. So I'm going to take up another applications of the stochastic processes, and I will focus on the stochastic model of some random phenomenon. And most of the systems or the situations are random in nature. That is, it change with time. So that's why the application of stochastic processes for those such systems, all such system, becomes very important, and application of stochastic modeling is being taken by the researchers, and of course lot of publications are being there during these, especially in the pandemic situation. Stochastic modeling can be applied to versatile system, lot of systems, whether it is a mechanical or electromechanical or electronics or a communication or any biomedical system or even human organs. So initially, when this area started from Second World War, the concept of modeling, mathematical modeling, and thereafter the model was constructed on the basis of the guess on the past experiences about a system. But in recent years, the stochastic modeling is being taken. Models are developed and analyzed on the basis of the real data collected from the system. So this come out to be a very justifiable way, and of course we dug out useful information about the system once you have the real data or information about the system. So taking care of this thing, I focus on the systems, their stochastic modelings, and of course taking real data. Now, what is the sense of stochastic modeling of system? So I will go with the very fundamental things, and then I will come to a situations where we can have application of these stochastic modelings. Stochastic modeling of a system.
Yes, sir.
Okay, sorry. The network connectivity was losing, so that's why. Anyways, so I'm taking care of a system which is nothing but you see collection of some components or elements, and that is working for some specific purpose. So system can be a way of doing things, or it can be a method.
Sorry to interrupt you, sir.
Yeah,
Please
please.
share your slide again.
Okay.
It is not visible.
Okay, let me reshare it. Is it okay?
Yes, sir.
Is it visible now, Dr.
Yes, sir.
Poonam?
Visible.
Okay, thank you. Now, when you talk about a way of doing things, so it can be a process or a method that can be taken. So these terms, of course, a system is defined in a number of ways, and this is, of course, the dictionary meaning, and that is Cambridge Dictionary. I had taken a source from there. Now, why we develop models, stochastic models, or even mathematical models? That develop models for any existing or proposed situation of the system. Understandingly, since that can be time can be discrete or continuous, state space can be discrete or continuous. Therefore, we can have four type of stochastic processes. That is discrete time, continuous state, discrete time, discrete state, continuous time, discrete state, and continuous time and continuous state. So that is a classification that already Professor Rao had taken up. Now, how we develop this model? For any, whenever you want to wish to develop a model for any situation or a system, how we can do that? The stochastic model, when you develop a stochastic model, the basis of the stochastic models are, the first thing is you must investigate the system thoroughly. That means that about a system, you should know what how that system works, what are the component of that system, how those components are arranged. That is, we can say the system's configuration or structure. What are the constraints, variables are involved? What are the outcomes of that system, and what are the relationship between the variables? That is the function between the variables. What are the controllable variables? What are the uncontrollable variables? So these things has to be investigated prior to development of any model for the system. And nothing but this is nothing but the, you see, the first steps or first phase for for developing any operation research model or any mathematical model. So once these things are clear, then before developing the model, you must be clear about the objective of the model. I have already listed in the previous slide what are the objective of the model. So what is your target? What is your aim for that developing that model? And further, you must be clear about what kind of models you are looking for. That is, whether it is a stochastic process applications for discrete versus discrete, or discrete versus continuous, or continuous versus discrete, that we have taken for such classifications. Moreover, the models may be the Markov models, as Professor Rao has already taken up. I have tried to skip those things which are already covered in this course. Of course, that was initially in my slide. I had deleted those because that has already been covered. So I'm trying to touch those part which is remain still untouched by Professor Rao or Dr. Poonam. So it can be Markov model or a Poisson process model or birth-death model. So that has to be decided. Then you can have a better models. And of course, for that purpose, you need to have comparison between the models. So that comparative analysis between and within the models for the existing and proposed filtration need to be done. That is all the basis by which we have the stochastic model developing. Now, how we carry out the analysis, what are the phases, what are the steps for the analysis of the model? So quickly I take the right from the beginning. First thing is the understanding of the system and its operation. What are the systems and their operations? It can be single system or multiple systems. Then you collect the relevant information or data from the system. Some parameters may not be known. You estimate by some statistical technique that you can estimate, evaluate the parameters of your interest. And on the basis of the variables and the parameters that you have estimated, you can develop a mathematical model. Of course, we need to have some assumptions or notations also. You develop the model. On the basis of models, you can have some mathematical equation, because we are talking about mathematical model or stochastic model. We need to formulate some mathematical equations. Then we have to solve these equations to obtain our parameter of interest, that is measures. And then using these whatever evaluated measures, you have to analyze the model using some appropriate technique or method. It may be a analytical technique, or it may be a numerical technique, or it can be a Monte Carlo technique. Then finally, the interpretation and conclusion about the system from the model. Now, whenever you develop a model, we have some measure of interest that is called system effectiveness measure or measure of system effectiveness or performance, which are generally taken up for any system. I'm talking about any mechanical or electromechanical or communication or even biomedical system or organ system. You see, when we talk about the medical sciences, that involves two things, two kind of systems. One systems are that system which are sportive system, biomedical systems, like apparatus, machines that are need for the sport of medical sciences. Maybe this X-ray machine or that CT scan screen, or even in terms of the consumer, that is the user. Now, some important measures I will like to explain, because these are very common and
Excuse
useful.
me.
Yes, please.
Sir, can you explain in short first passage time?
Okay, I will go one by one.
Yes.
I'm
sir.
just
No.
starting with those very important out of these one. Okay,
Right.
I will take care of the first passage time.
Right. Sir.
But you see,
Thank
at the back of all these things is the reliability of the system or system reliability. You see, this is also known as a survival function. Survivability of the system. If it is a, you say, living system or human organ system or human system, then we can say consider this as a survivability of the system. So what is that? the period under specified operating conditions. You notice here three things. One is that this is the probability. While discussing the survivability or the reliability of a system, we are taking care of those systems which involves randomness and uncertainty. And that's why we are talking the probabilistic concept here. Second thing, that particular system should give satisfactory performance for a specified period. Now, the time is involved. The specified time period can be, say, 1 day, or it can be 1 month, or it can be 5 years, or it can be 10 years, or 100 years. The performance should be satisfactory. Now, what is the measure of performance? That is also very important. The performance depends upon different measures. You can have different measures. Someone is interested that the output should be good. That is, number of output should be more. The other can have a performance in the sense that the quality of the product should be good. And or one can say that the output may result into lesser cost, and so on and so forth. There can be different way to look into the performance. And the last thing is the operating condition. So if you shift a system from one place to another place, or to one environment to another environment, the system's performance may change. So we have to take care of that, the operating conditions, under what conditions the system is operating. So first thing is the probabilistic in nature that system is, and that's why we are taking the probability. Second is the performance for a specified period, and thirdly is the operating condition. Now, mathematically, if we take this system reliability or reliability of the system, I just take this in a mathematical formulation. If I say that capital T is the lifetime of a system, then the reliability of that system, that is, that system works satisfactorily for a specified period. So let me take that small t, that period as a small t. So the interval 0 to t. So up to t, that if we are talking about the reliability, then the reliability plot FD, capital FT, that is CTF of t. And you know the exponential probability density function is given by Ft is equal to lambda e power minus lambda t, where for all t greater than equal to 0. So in that situation, if small ft is equal to lambda e minus lambda t, the capital Ft, which is nothing but the probability that capital T is less than small t, is evaluated as a 1 minus e power minus lambda t. And the complement of this is reliability, capital RT. So which will be given as e minus lambda t. So if we plot Ft, which is shown here in the graph, so over the year, over the time, the reliability of the system decreases, which is represented by a green line. Whereas the CDF of the failure time, is it clear? It is a timeline. So it is of course a continuous line. So I'm taking interval from 0 to t, and if lifetime of the system, capital T, is more than this t, then the system has reliability up to time t, small t. So this system is reliable. Is it clear?
Okay.
Now, if this t, small t, approaches to infinity, in that situation, this reliability will go down and ultimately approaches to 0. At epoch 0, this will be 1. Is it clear?
Yes.
We will state by the example also. Mathematical situation will take care. Now, one of the thing was asked me is the first passage time. You see, these are a few terms which are very important for any system analysis, and one must be clear, one must understand. If someone has a doubt, you must ask me. First passage time, if I talk about, you see, at any time, say system is at the state J. Now, mathematically, if you wish to compute this, if capital T is the lifetime of the system, then the reliability function RT, we have already mentioned, it is nothing but 1 minus Ft. where ft is the failure time distribution function, and the probability density function is nothing but the differentiation of this ft, the first derivative of ft, that is the pdf. So this is the relationship between the pdf and cdf for failure time. So ft is the failure time density function. So if you are interested to find MTSF, which is defined as the expected time for which the system is in operation, so that will be given by the average value of the time variable. You see, whenever we compute this thing, we are looking for the average value. So say I take 4 systems.
So
Notice
please
it.
give me one example.
Okay, I'm giving you example. Say there are 4 system fails in say 16 months, and third system fails in say 2 years. I'm just taking a hypothetical system.
Okay, sir.
So what is the average time before it fails? So that average time has to be computed. Since time is a variable, continuous variable, note it. It is not a discrete variable. We are taking here time as a continuous variable.
Yes, sir.
So therefore, what will be the average value? That is of over interest. Any company, before providing any guarantee, they evaluate their system, they test their system, that how long it will work satisfactorily, so that we can provide the consumer guarantee. Even when they provide the guarantee, some system fails. Even it can be 1% or 2%.
Yes, sir.
So our interest is to look for the reliability measure of that system. Is it clear?
Yes, sir. Good.
So that time, any system can fail anytime. That's clear. And if you have a multiple operation, multiple experiment of that system, then you can have the average value of that time before it first failed. Now this RT, which is a function of time. So once it is there, then whenever you are interested to find mean time between the failure or mean time to system failure, mathematically, how will you compute it? So therefore, the formula for that is T into Ft dt. This is for any continuous. Whenever you have any continuous variable, say x is a continuous variable and fx is its a probability density function, then integration of all value of x fx dx provide you the mean value of the random variable. So here we are taking the mean value of the time, failure time. So that is MTSF 0t tft dt. Now, if we put the value of ft, ft is nothing but the derivative of ft. You just place here value of ft as a 1 minus rt. So this is nothing but the rate of change of the rt. And if you simplify this, this is nothing but the integration of rt dt. So one can see that MTSF is directly proportional to rt. I can say that the MTSF is the integration of rt, or RT is the rate of change of MTSF. You see, differentiation and integration concept you can apply here. So if you are able to integrate RT function, then you will find MTSF of any system. Now this is sometimes difficult, then you can make use of Laplace transform, which is a way to simplify this. We can also write this integral 0 to infinity RT as limit s goes to infinity r starts s. Laplace transform concepts that we can apply. So anyway, if you can integrate, then it's okay. If not able to integrate, if a complicated function is there, then you can take Laplace transform of the reliability function, and that is the relationship between MTSF. My interest is to find out, you see, RT. So I can just rewrite this function in this form. This R, if I represent phi 0t as the cumulative distribution function of the first passage time, that's why the reliability function was defined first and the first passage time was defined at the later stage. These two things are related to each other. Once you want to evaluate RT, we need to have this phi t. So if phi 0t be the cumulative distribution from the first passage time from the initial stage to a failed state, then this R star S, this limit s goes to 0 is not there. It is only 1 minus phi double star s. So this is a Laplace tilde transform of phi 0t over s. So we have applied this, and this is the formula to compute MTSF. And here you see, you don't take a limit here, it is in fact here limit S goes to 0. So R star S is nothing but 1 minus phi double star S over S, and we place this here in this formula, then MTSF will be given as limit S goes to 0 of 1 minus phi double star S over S. So phi star S is Laplace transform, and phi double star S represent the Laplace Stieltjes transform, LST, of phi 0t. So that way we can compute MTSF. So you see, this is the formula to compute reliability and the MTSF of a system. Now let me take the other part. We have taken any system without considering into, say, its repair part. Now, for any system, you may not be interested to see the performance of the system for a longer period of time or for a time interval. You may be interested to look the performance of the system at particular epoch. आज ये सिस्टम काम कर रहा है कि नहीं कर रहा, अभी कर रहा है कि नहीं कर रहा. Suppose a patient shifted to a hospital, whether a particular machine is working or not, that is more important. How long it was, for long, what is the reliability of that system, that is a separate part. But the moment it is required, system is need to be operated, it is available or not. So that is also uncertain, and therefore the availability of the system, any system, is defined as the probability that the system is operating satisfactorily at time t. So this is at a particular point time t, whereas the reliability was a measure, a probability from 0 to t, probability that the system works satisfactorily from 0 to t. So that is a concept with the interval performance, whereas the availability a concept related to a point performance. So that is the difference between the reliability and availability functions. So that's the point I have mentioned here. The reliability is an interval function, whereas the availability is a point function, describing the behavior of the system at a particular time, specified epoch. Second thing is, reliability function precludes the failure of the system during an interval. Failure of the system during an interval, 0 to t टाइम में फेलियर नहीं मान रहे हम. जबकि अवेलेबिलिटी की जब हम बात करेंगे तो where I am writing the component as a unit 1, unit 2, unit 3, unit n, it can be element or component. So once these units are in series, so this is a system with series configuration. For example, if you have an aircraft electronic system, in an aircraft electronic system, the system that are in series are sensor subsystem, guidance subsystem, and computer subsystem. These are in series. If any one of them fails, then aircraft electronic system will fail. This is the disadvantage of arranging or structuring the system components in series. If any one of the unit fails, the whole system will fail. So here you notice that the whole reliability, the reliability of the whole system will depend upon the reliability of each of the unit, each of the component. So for any of each unit, if I say that RIT with the reliability of the ith component or ith unit, then if there are n units, n components in the system and they are independently distributed with density FIT, that means that the first component say have the failure time distribution FIT, F1T, second component has say F2T, third component is F3T, and so on and so forth. If FIT is the PDF of failure time of ith component, then CDF will be given by capital FIT. Then we can compute the reliability of the whole system, and the reliability of the whole system, say RT, will be nothing but the probability that the lifetime of the system is more than T. So we had to tell the first, or the second, or tell the nth. So that reliability for each of them we have to take up, no? And that's for the product is. Suppose you are taking probability A intersection B. What is the sense of A intersection B? Joint probability of A and B. Probability that A into probability of B. That is the both the system work simultaneously. A as well as B or both. The system they are in parallel. If any one of the system fails, then the whole system will not lapse. The whole system will not break down. So in such situation, we have more safety, more reliability. For example, if you have an aircraft having two engines, if one engine fails, even then aircraft will work. In the human body, you see, we have two kidneys. So system, both the kidneys are working. Even if one has damage, the system, the human body works on kidneys. But if both the fails, in that situation, the system may fail. So that is the story here. If all the n component fails, only then the system will fail. This is the advantage of parallel configuration. In some system, we have such a configuration. Now, if this is the story, then in that situation, the reliability is more, but we can also compute the reliability in terms of their individual unit reliability. If RIT represent the reliability of the unit or component and TI be the lifetime of the unit in time t, then the system reliability again using the RT probability that t is greater than t is now it will be the maximum time. Notice it, there it was a minimum of TI t to Tn. Now it is the maximum of t because the system go on working till the last component works, last unit works, and therefore it is a maximum of greater than Ti. But we write this thing in a complement form. I can also write it as a 1 minus probability that minimum of Ti's, that is less than T, less than equal to T. And therefore, each of them is less than equal to T. Again, we use the probability law, multiplicative law of probability. So this will be the probability 1 minus P T1 less than equal to T into probability T2 less than equal to T, and so on. But probability T1 less than equal to is nothing but 1 minus R1T. Probability T2 less than equal to T is nothing but 1 minus R2T. And therefore, we can write it as a 1 minus product of the complement of reliability of each unit. And that's why it is 1 minus product of 1 minus RIT. So this is the situation whenever this is a parallel configuration. But interestingly, this happens in very simple situation. Very simple situation is for series configuration. And in a parallel configuration, we have more components, of course. They are working in parallel. And whenever it is a mixed configuration, then the model, when the system becomes complex, some components are in series, some components are in parallel. So that is called hybrid configuration or mixed parallel configuration. Their reliability computation becomes a little bit difficult. However, we can compute that. Now, I quickly, because the time is also running short, I just go for the redundancy. Redundancy, the concept where we have available spare units with the system. Just like in a parallel system, we have additional components. However, they are working. System will go on working till you have spare units. For example, if you have a automobiles having multiple or a spare tires with you, a stepney, the system is working on tires. The vehicle is moving on tires or wheels. And if one of the tire punctures, then stepney can be replaced and the system moves on. So that stepney is nothing but a redundant tire, a spare tire. So in that situation, the system's operation may be continued using those spares. So this help us to have more reliability of the system. That is, the system operation can be extended to more time. These redundancy are different kind of redundancy. We can have active redundancy or passive redundancy. Active redundancy means both the units, which are whether it is a spare one or not, they are working. They are working in the same fashion the original unit works. Passive redundancy where the system one unit is in spare. So this kind of you see, I will share with you the slides for these. You can go through, and of course the passive redundancy, and I just want to touch upon that how we have the advantage of learning these things, training of these things. Once you are aware about this, then we can develop models. I'm just illustrating this thing with the system. Say I have taken an example of a base transducer system which is commonly used in mobile communication systems. If we want to develop the model for that system, what information we need to have about the system, we need to investigate the system, we need to have a data collection for the system. So what is the design architecture of the system, how many component units are involved in the system? These are the questions to be answered before developing the model, stochastic model. How the system operates, under what environment system operates, how long it remains in operation, what are the different kind of faults and failures in the system, how the system is being maintained or repaired, replaced, what are their policies, how much time is taken to repair or replace or maintain the system, what are the cost factor involved, what are the kind of repair facilities or service facilities involved there, and what are their nature. They are single repair facility or multiple repair facilities, whether it is a hot redundancy, warm redundancy, or cold standby. So these question has to be answered before developing a model. So this is a communication system. You see, this is the basis of a communication system. Any communication system involved a transmitter, encoder, channel, decoder, and receivers. If a system works without noise, then there is no component of noise. But if this is the uncertain factor which is involved in any communication system. So I'm just giving you the views of the slides of a mobile communication system. I'm not going to depth of this. You see, before going to study this system, we have to got a complete information through the literature as well as from the company. Mobile equipment is nothing but the mobile set you use where the data is transferred, whether it is a voice data or it is a video data. The base transfer system is the, you say, base transfer station. Your mobile voice, mobile data shift to this BTS, and from BTS it is goes to BSC in an operation system, and then from BSC to it goes to MSCs. I'm not going to the depth of this, but my point is that for any system, this is a work of one of my student who has worked on this communication system and BTS. She has visited the system, gone through the literature of the system, and then visited that system, and how the Vodafone Spacetel Limited is using this BTS. You might heard about the towers, network towers for mobile communications. In there, BTS is involved. Basically, BTS is nothing but a, you see, if it our part is seeing, this is a BTS. We have to, you see, look into the working of this system, their operations, what kind of the faults in these systems are there, major fault and minor faults. We have gone through what are the different other problems then incurred in BTS, and that is queuing delay, packet loss or blocking of some new connections, and that lead to traffic congestion in of a system. These are some technical terms which is understood through the help of the communication engineers in the company. And after going through the detailed observation of the BTS, collecting data from the BTS, from that company, and data you can see that different kind of faults over the period of time, minor fault or major faults, how long that fault goes, how that works, what policies adopted to work so that repair that fault, whether it is a hardware fault or software fault, because the mobile communication system is a system which involved both hardware as well as software part. So that is a hardware software system. We have estimated the important measures that are related to.
Sorry to interrupt you,
please.
sir. You are running out of the time.
Yes, that's the point.
So please wind up in 1
Okay.
minute.
I'm just showing the slide
Yes.
that how we can have the analysis of a system using real data. We have computed these measures that I have already explained. This was the company we have visited and collected data. On the basis of that, the models are developed. You see, before developing a model, we need to have some assumptions about the model. The model's assumption have been highlighted here on the basis of minor. So these are the some notations we have taken for the model. And this is a state transition diagram. With the help of that, we can have a TPM, transition probability matrix, or Markov chain, using the concept of Markov chain. Markov chain already been discussed by the Professor Rao. We can have these probabilities of transition. We have computed probability of transition. And these are the transient state. And of course, we can compute the steady state, taking limits. And these are the relationship to verify whether the probabilities are 1 or not. We have computed mean time to system failure, expected uptime, that is availability, expected degradation time, downtime, congestion time, and the busy period of the analysis of the repairman. And for repair time, for inspection time, and the cost function, we have also highlighted, and on the basis of that, the system is analyzed. I'm just giving you the outline of this an example that how this works, and this paper is already published in one of the reputed journal. You see, this is the one model we have constructed for the situation. Another model can also be constructed taking care of the other observations. This is another model for the same situation, same system. But here the new variables are introduced, new situations are introduced, and on the basis of that we have this model. And we can kind of find out the cutoff points of this paper are already published. If you wish, I can provide you the reference of these papers. Similarly, you can have the other system also, not only the communication system or BTS system. We can also have such modeling for industrial process water system. This is a thermal power plant system. We collected the data, real data from the system. We measure parameters related to our interest. We describe the model. On the basis of the model, we have state transition diagram, and we have calculated all the performance measures. And we have such two models for this thing also. You can have a multiple model, but you see at the last, you can also compare the models, which model is the best for all those situations, taking care of all probable situation of that system, and we can locate the best one. These are some books that can be of your interest to go through the concept of stochastic modeling for the system or for a situation. You may note down, these are well-known books which are available with the well-known publishers. These are also, some of them are available online. So this is all about for my talk. Of course, it is a little bit more time has taken because of some network issues. But I will be happy to answer the questions of the participants. Anyone? Any question?
Sir, I have sorry.
Welcome.
Sir, based on the real data, how to find out that the failure time follow exponential distribution or arbitrary?
Okay, very nice question. You see, whenever you observe any system, two things has to be seen. How the system works. That is, what is the failure pattern of the system. Failure pattern of that system has to be plotted. So if failure rate is a constant for any system over a longer period of time, if it is a constant, for hazard rate or failure rate is a constant, in that situation, the failure time distribution is exponential.
Okay, sir.
You can, if you understand, you may go through the books. Already Professor Rao have mentioned the books by Lawless. You can also go through the book by J. Mehdi, and also one of the book by S.K. Sinha, that is on the survival analysis. So if you have a constant hazard rate or failure rate, the time distribution will be always exponential. This is one way. If you are not aware of the failure time, then the other way is to use the software to test whether the random variable generated by the system, that the failure pattern generated by the system, is a exponential fitted or not. We have software, whether the exponential distribution is fitted to the failure date or not. We can use that.
Sir, which software?
I will mention you that I will give the details of the softwares which are available with us. So this is one way. Second thing is, if failure pattern is increasing or decreasing, in that situation we'll be having the generalization of exponential distribution. It can be Weibull distribution, it can be gamma distribution, it can be Rayleigh distribution, depending upon the situation. Some model, in some cases failure rate is increasing, in other cases it is decreasing, and in some system also it is sometime increasing, sometime decreasing. That is a bathtub curve pattern.
Yes, sir.
There Weibull distribution is applicable.
Okay, sir.
So all one thing is you go through the pattern of failure rate. The other thing is you use software to test whether the failure pattern having fitted a particular distribution or not.
Okay, thank you, sir.
Yes.
Thank you, sir.
Any other question? Okay, thank you very much for this session and patiently listening to this my presentation and this talk about. I just share about the system in the next next lecture, which is for tomorrow only at 5 to 6. I will take up only the human organ system or hospital systems. There we can apply how we can apply the stochastic modeling and we can carry it out analysis. Thank you very much and sorry for, Professor Rao if you are connected. It had taken a little more time.
No problem, Professor Kumar. Let the.
Thank you so much.
Yeah. Thank you.
Just
Thank you so much, sir. Now there is a announcement for the part.